we're going to discuss computer memory today. So, the structure of this module, we have been building up. We started off on the ground. We've been looking at transistors. We've been looking at making logic gates out of transistors. We've been looking at making simple machines out of those logic gates. We've been looking at representing data using zeros and ones, Boolean coding in logic gates. The last two lectures, we put it all together and we were looking at the structure of a CPU. We saw how to take those simple machines made out of logic gates and make them into subcomponents of the CPU, like the arithmetic unit, the control unit, the registers. Last week, we looked at some more advanced contemporary CPU design. That's really the peak of the course. Now we're going to come out of the CPU. We're going to look at memory today, then we're going to go further out, we're going to look at input-output devices, we're going to get into embedded devices, parallel computing, and so far. So we've just got through the main meat of it in the CPU lectures, hence we get our musical reward today. So, today's lecture is all about the concept of memory. Computer memory is organized quite like physical memory that you use on your desk. If you're an office worker, you probably work in a room somewhat like this, and you can see there is information in different locations relative to where you're sitting in your office. If you're sitting in your chair, you have information right in front of you. This is like the registers of your computer, pieces of paper that you're working on right now, things that are getting transferred in and out of that working pile. You might have other piles of books that are close by on your desk. You can go and reach, you can fetch a book, bring it into your working area, like your registers, and do some work on that. If we look further away from those, you can see that there are shelves of books in this office. You might have to actually leave your chair to go and fetch these, but a shelf has a higher capacity than a pile of books on your desk. It's a larger memory, but it's slower to fetch it. You can go even further. You could consider, if you run a small business, you might have boxes of old accounting files that you keep in the attic. You only have to get those out very occasionally if the tax inspectors come. There's information you use that is even further away. There's things that only exist in your local library or your bookshop. You have to leave your house to get that information. If you're doing research and you need something really obscure, you take a train to London and you go to the British Library where they've got everything in a great big building there, and in underground storage facilities outside of London. So there's a relationship between the size of memory and the speed. You can have small pieces of memory that are very fast to work with, that are close to you, and you can have bigger but slower memory as you go further away. So this is the same structure that we use in computer architecture to organize memory. We can make a distinction between primary, secondary, tertiary, and offline. So primary memory is the system memory. It's what we would normally think of as forming the computer. This includes the registers, and it includes the RAM. It includes what are called caches, which are layers of memory in between the RAM and the registers. Secondary memory is stuff that is connected to your computer, but not part of the RAM system. So usually this means that either a spinning hard drive or a solid state hard drive nowadays. You have to bring that into main memory when it is needed. Then we get to tertiary memory, which is, it's called nearline. It's almost online. So you can have machines like a robotic jukebox full of CDs or Blu-rays that can be quickly brought into the system and brought online. Then you get to offline storage, which is completely archival. This is where you write your data onto some media, like the accounting boxes in your attic, and you put that media in boxes in your attic for backup purposes. So everything about memory is structured around this pyramid concept then. You have small and fast at the top, things like the registers in your CPU, made of flip-flops. The RAM is what we normally think of as computer memory, somewhere in the middle. You've got your hard disk, your secondary storage, and you've got your tertiary and offline storage. So when you're dealing with registers, you're just dealing with maybe hundreds of bytes nowadays. When you get to offline storage, you're dealing with petabytes. We'll talk about the definition of terabytes and gigabytes and petabytes in the next slide. So when we discuss memory, we have to work with very large numbers, especially when you get into big data systems, cloud computing, where you're dealing with whole rooms full of data storage devices. The way we measure storage has become somewhat confused due to a conflict between decimal notation and binary notation. When you talk to real scientists and engineers, like physicists, they have a committee called SI, the Système International, and they standardize the units that everyone is supposed to use in those fields. And they like powers of 10 and they like powers of 1,000. So if you're doing physics and you talk about a kilo something, like a kilogram, that means you have exactly 1,000. And if you talk about a megagram, that would be 1,000 thousands or a million. And you can go through kilo, mega, giga, tera, peta, exa, zeta, okay? These are defined by the SI as units of 1,000. The natural unit of memory is the bit. The bit is a single Boolean 0 or 1. So we should really be talking about terabits and petabits. This would be the official SI view of the world. Everything is in bits and then it's in powers of 1,000 bits. We have this historical hangover that people still think a lot in bytes. Now, historically, this was very useful because if you had a BBC Micro that had a 64-bit address space, but every member of that address space was storing an 8-bit word, also known as a byte, you can multiply the number of addresses by the word byte. So when they say it is 64K, they mean it's 60, not quite 64,000, I'll come to that in a moment. There's about 64,000 address spaces and each one contains 8 bits, so you have to multiply your 64,000 by your 8 to get the total number, but you can say 8 kilobytes, which refers simultaneously to the overall size of the memory in bits, but also to the number of address spaces, how many words are there. On a modern computer, the concept of a byte really has no meaning at all nowadays. Until we had Unicode, you could just about argue the byte was still relevant because 1 byte is an ASCII char. But nowadays everyone is using Unicode and our word lengths are no longer a byte. A 64-bit machine is a lot of bytes. So there's really no relevance of a byte at all. And we could argue that the concept of a byte should be retired nowadays. We should be measuring everything in these SI units and bits. Now, you'll also come across names like this, kibibytes and mebibytes and gibibytes, okay? Again, this is something of a legacy. It turns out if you take 2 to the 10, you get 1,024, which looks a lot like 1,000. And so it was common, especially in the 8-bit era, to refer to this number as a kilobyte. It's a little bit bigger than an SI kilobyte, and it's a power of 2. And you can go on building these up. If you have 2 to the power of 20, you get a mebibyte, 2 to the power of 30 will be a gibibyte, and so on. In architecture, these terms are probably more useful than in other fields of computer science, like data science. In architecture, you're often dealing with things that are inherently powers of 2. If you're working with address lines coming out of your CPU, that inherently defines a power of 2 address space. So you will sometimes see these numbers. Nowadays, we are supposed to call these kibi and mebi and so on. These new names were standardized in 1998. Historically, the SI names were used to mean these powers of 2, and you'll still see manufacturers trying to confuse you nowadays. They'll sell you something that claims to be a terabyte hard disk, and it's actually a tebibyte hard disk. And they'll always pick whatever number makes their product look the best, and then you'll install it and you'll be confused because you see it's slightly less than you thought it was going to be. The networking people and the data transfer people do tend to think more naturally in bits rather than bytes. So it's common to write bits as a lowercase b and bytes as an uppercase b. If you're measuring things like broadband speed, you probably measure that in megabits per second rather than megabytes. So we should really be doing everything in SI units and bits rather than bytes nowadays. But I've yet to see anyone advertise a 10 tebi-bit hard disk. I don't know if anyone would ever actually buy such a thing. Anyway, let's look at the memory itself. Most computer memory nowadays is based on the von Neumann architecture. That means it is holding both the program and the data sitting in the same place. Usually the RAM is sitting on some chips, Usually there's a CPU, and traditionally you have something called a cache, which sits between the CPU and the main RAM. It makes a copy of stuff that you're currently using, and it keeps it in a smaller, faster place. It's like the desk analogy. It's like bringing books off your bookshelf and putting them on the sides of your desk to make them more readily accessible. Computer memory is often thought of as a bunch of pigeonholes. Pigeonholes once literally contained pigeons. They were used for nesting them. To pigeonhole someone means to put them in a mental stereotype box, like one of these pigeonholes. You know, I'm studying real computer science because I don't want to be pigeonholed as a JavaScript programmer for the rest of my life. We still use pigeonholes here in our school office. If you look at our mailboxes, they have the same structure. They have people's names in alphabetical order. Computer memory is just like this. It's a bunch of slots. Each slot on a computer contains a word. And remember, the word length is given by the bits of the machine. So a 64-bit machine has 64 bits in each box. And each box in the computer has a number instead of a name, usually written as a hex code. And that's called the address space, all the places that things can be stored in the memory. Sometimes we'll draw memory like this then. We can say each memory address has a number, usually written as a hex code, and it has a content, which is containing a word. Okay? 8-bit computer holds 8-bit words, 16-bit computer holds 16-bit words, and so on. Why do we use words? In theory, you could address every individual bit in memory, but it would be impractical to do that. It's very rare that you ever need to read and write a single bit. You almost always want to read a word-sized chunk of data. And we can set up the hardware to do all this in parallel. So if you request a word from memory, it's just as fast bringing it into CPU as bringing a single bit. The address space is shared between every component of memory that is using it. So in particular, you have both ROM and RAM in there. ROM is read-only memory, so this can include chips with code that is burned onto the chip that cannot be changed. The ROMs will appear in the same address space as everything else. In the old days on the BBC Micro, you would know where your ROMs were. There were parts of this address space containing particular functions that were physically sat on chips. And so you'd call those functions if you wanted to make a sound or call a graphics command. Those commands were physically located on chips in ROM, and you'd call out to those addresses and run some code, and then come back to your user code. So ROM and RAM are the yin and yang of computer memory. They are both almost entirely misnamed nowadays. RAM stands for random access memory, which in theory means memory where it is as fast to randomly access any point as any other point. Okay, something like a cassette tape is not a RAM because it's faster to access things that are nearby on the tape. You access it sequentially. That's a sequential memory. So in theory, RAM is anything you can randomly access at the same speed. That's not how people use the word RAM, though. RAM is used to mean a particular kind of memory that has a bunch of additional characteristics as well as being randomly addressable. So it's memory that is directly accessed by the CPU. It exists within the address space of the computer. It is both readable and writable. And it's volatile, which means when you turn the power off, you lose everything that is stored in it. Okay? And we use RAM to hold data and programs in our von Neumann machines. So the name random access only refers technically to one part of that, the fact that it's randomly accessible, but it's inherited these other meanings that everybody uses. Okay? So we've already seen some RAM in the analytic engine. Remember, Babbage was using these rotating gears to store numbers. You read off the numbers by spinning a pole by 360 degrees and putting it in contact with the place you want it to go. And that will read off the number and transfer it from a source to a destination. Remember, that was a destructive read. When you do the read, you're destroying the original copy of it, and you're literally moving it to somewhere else. Historically, we've also seen systems like acoustic mercury delay lines. So we talked about the idea of using musical feedback as a form of memory. If you take a microphone and a speaker and shove them next to each other, this system can have two stable states. Either everything is silent and it remains silent, or everything is loud and screeching and remains loud and screeching due to the feedback. that notion of acoustic feedback can be used to store a 0 or a 1. The presence or absence of the sound is the 0 or the 1. And it was found that if you place your microphone here and your speaker here, it was found if you fill the gap between them with mercury, that delays the speed of sound and it gives you a longer term memory. If you didn't fill it with mercury, you'd need a much longer acoustic tube to make this work. We've also touched on memory using CRTs. These are cathode ray tubes. These appeared in the Manchester Mark I machine. They're the origin of the green text in the matrix and on our VI terminals today. Originally, those cathode ray tubes were not used as a visual display. The visual property of them was just a side effect. They were really being used to store memory. It was found that every pixel on a CRT would persist for a little while. You could light it up and it would persist, and you could have it persisting for just long enough that you could look at it, read it, see what it was, and then write it again and keep it persisting, forming another kind of feedback loop. So initially, these green screens would have been full of random-looking dots representing the zeros and ones of the memory. It was only later people figured out they could play Space Invaders by reading and writing in particular locations corresponding to coordinates on the 2D screen. But the kind of RAMs we have now are electronic. They come in two basic forms called static RAM, SRAM, and dynamic RAM, DRAM. The static RAM is smaller and faster. Dynamic RAM is the main big RAM. If someone says you have 4 gigabytes of memory, they mean the DRAM in it. Static RAM is usually used for these caches. It's the smaller, faster memory for working with. So, sorry? That would be DRAM. Yeah, the stuff that goes in the slots is DRAM. Okay. SRAM is going to appear on the cache. So we've already looked at how registers are implemented in the CPU. You can build a register out of flip-flops. Flip-flops are fast and they're quite expensive to make. There's quite a lot of transistors going to making a flip-flop, as you'll have seen when you build one out of logic gates. Dynamic RAM is different. It's based on capacitors, which are a different kind of electronic component that we haven't seen before. And they're slower, they're more analog, but they're very cheap to make. They're structurally simple. Yeah, so the stuff that you put into your slots is going to look like this. You can see there's a notch here. The position of these notches is important because it tells you exactly what flavor of DRAM you have. The stuff that's going to make up your cache is probably going to look more like this. So a couple of you have already built one of these in Logisim. You can implement SRAM out of flip-flops and using decoders. So the decoder enables you to select a word from an address. This particular form then, we have 4 words of memory. Each word is 3 bits. Okay, so each column of the image is a word. The logic down here is taking a binary description of the numeric address you want to go to. So you might want to go to address number 210. That is going to translate the binary coding into a single line. It's going to light up one of these lines and the other lines will be off, and that will activate the array of flip-flops corresponding to the word. Okay? So SRAM is taken to mean this structure then. It's using flip-flops as a CPU register would use, but it's also using this addressing structure. It's also taking words, decoding them, and mapping them to words in the memory. That's static RAM. So it's very, very fast because everything is made out of digital logic. The state is stored in the activation of the digital logic components of the flip-flops themselves. But it's expensive because there's a lot of transistors in each of these flip-flops, and there's also a lot of transistors you need here. As you get more and more bits, if you have 64 bits of input, this decoding logic becomes very heavy and non-trivial. It's not practical to build a large RAM with a decoder that size. So when we need the big RAM in our computers, we go to what is called dynamic RAM, or DRAM. So DRAM has the same addressing structure. It has the same concept of words being stored at locations. You can see the same array structure here as in the SRAM figure. But what you have now are different components implementing each of the bits. Each of these squares is 1 bit of data. So this is a transistor. We've already seen transistors. There's on-off switches. This thing is a capacitor. So a capacitor is it's a break in your electric circuit with two big metal plates that don't quite touch each other. So current cannot flow across a capacitor. It's a break in the circuit. But a capacitor will store charge. If you make the plates big enough and close enough, you can put current on it, and electrons will accumulate on one end, and you'll accumulate holes on the other end. So whether or not the capacitor is charged up is used to store the 0 or the 1 in DRAM. Now, capacitors are inherently analog devices. They take time to charge and to discharge. This makes them slower than flip-flops. But they're much cheaper to implement. You can see there's just less stuff in this figure. We can see the individual transistors and capacitors, whereas the SRAM, you're still working with logic gates, and each of those logic gates has to break down into transistor. Also, due to the nature of capacitors, they have a property similar to Babbage's engine, which is when you look at them, they discharge. If you connect the charged capacitor to your circuit to read it, the electrons will flow away, and that can destroy the number that was originally stored there. They also discharge naturally over time, and so you have to refresh them. Like on the CRT memory, you have to keep looking at them, saying, what is it, and then rewrite the value on the capacitor. And this takes time. You have an ongoing problem with DRAM that if you try to read something at the same time that it's getting refreshed, then those things will conflict, and your CPU has to stall because it's waiting for the refresh and then waiting for the read to come afterward. So what we're seeing in fancier modern CPUs, we talked last time about pipelining and out-of-order execution and prediction. You see these prediction engines getting put into CPUs now. They try and predict way ahead in the program what memory is going to be needed. Maybe 10 instructions ahead of what's currently in the pipeline. And then you can go and tell the memory controller to get things ready. You can start it doing the reads. In particular, you might want to start reading out of DRAM and moving it into your cache in SRAM as early as you possibly can. You want to have everything ready in some higher level of cache before it's actually needed. Something to watch out for when you're programming with DRAM is the way the addressing works. Typically, we don't address each word via a single monolithic address as we do in SRAM. In SRAM, this decoder takes every binary code. It has a lot of digital logic here, and it goes and activates that location. What you get in DRAM is an array structure where the address is split into a row address and a column address. Okay? Your memory controller will split up the address into those two parts. Half of it will go and light up a row, and half will light up a column, and where they both meet, that unit will get activated. The consequence of this is that it's faster to do a whole bunch of reads from the same row. If you're reading contiguous parts of DRAM, a lot of the work is done in activating the row in the first place. Then it's quite cheap to read the individual columns out of it. So if you're really trying to hot rod your machine, you want to be arranging your data so that everything is stored in these contiguous rows, and you want to be pulling whole rows out of DRAM at once. This will work very well with the caches that we'll talk about next. Okay, so someone was asking about different types of DRAM. Yeah. So DRAM normally looks like this. It goes into slots on a motherboard, on a traditional desktop at least. These slots are standardized according to various standards that have evolved over time. You still see occasionally machines using SIMs. These are really a 1990s thing. They have a particular form factor. They have a particular notch here, which means they only fit in a certain kind of slot in a certain orientation. And they have a 32-bit bus width, coming from 1990s 32-bit machines. When we moved to the 64-bit era, we went to DIMMs. DIMMs have roughly the same form factor, but it's distinguished by the notches being in a different place, so they only fit in a dedicated DIMM slot. They look as if they have the same number of pins as the SIM. They look as if they still have 32 pins, but they're double-sided. So in a SIM, the pin is the same pin on both sides. On a DIMM, it's two different bits of metal on the two sides. That's what doubles you up to getting 64 bits. This is what you'll typically see in your desktop machine today, maybe storing 32 gigabytes on what is called a module. That's a bunch of DRAM chips put together on a small circuit board that plugs into your motherboard. DRAM has evolved over time. There's obviously a lot of commercial interest in this. Fundamentally, the bandwidth, that's the amount of data per time that can be transferred. It's given by a product of the bus width, that's how many bits the memory is. The speed that you're running at the memory at, which is probably not the same as the speed of your CPU. CPUs go much faster than memory. And then multiplied by what's called the data rate. That's how many times we can use the memory per clock cycle. So we started off with what's called SDR, single data rate DRAM. In this case, your clock was going like this, and every time you had an uptick on the clock, you could do a read or a write in the DRAM. That then got doubled up to what's called double data rate, or DDR DRAM, which means you can do stuff both on the rising and the falling edges of the clock. So it's the same clock rate, but you're doing twice as much within each cycle. And since the invention of DDR, or what is now called DDR1, the technology has evolved through several standards set by a bunch of companies agreeing with each other. We've seen DDR2, 3, and 4. These do a combination of increasing the speed, increasing the data rate, and taking advantage of every advance in manufacturing technology. And again, they're all distinguished by the position of these notches. Each iteration has moved the notch a little bit to prevent you putting the wrong kind of card in the wrong kind of slot. Okay, DRAM is pretty reliable nowadays. Didn't used to be, it's become more reliable. But for a few applications, we need even higher confidence than you get in regular DRAM. As with CPU design, everything is getting smaller. We're getting closer and closer to the atomic level. At some point, we're going to be in a situation where one atom is going to have to represent one bit. And when you reach these levels, you can run into problems with interference, specifically from cosmic rays. Now, the Earth's atmosphere shields us from most of these, but there's still a whole bunch of electrons and muons and alpha particles getting down here very fast. If you build a cloud chamber, if anyone's been to the museum in Edinburgh, the Science Museum, there's a lovely example of a cloud chamber. You can actually see individual muons and alpha particles leaving traces in a very small cloud chamber. If cosmic rays like that hit your bits being stored in memory, they can knock things out of their position and they can flip the bits, they can flip zeros and ones. This usually isn't a big deal, but if you're doing something really critical, if you're hosting the world's biggest website, or if you're running an in-memory database where you're relying on the memory to host the real data rather than hard disk, if you're dealing with governmental stuff, important finance stuff, and most relevantly, if you're doing embedded systems in space, if you ever build something that goes on a satellite or a Mars rover, these are going to environments that don't have the benefit of the atmosphere, reducing the cosmic rays, so you're going to get hit by a lot more cosmic rays. So it's a classic problem with these people doing cameras on helium balloons that they try and get into space, that they don't think about the memory. You need to take some protection there. So in these kinds of cases, we have what is called ECC RAM, which is error correcting code RAM. This uses some extra bits to store checksums of the data. You're building in some redundancy to your storage. That means if one of the bits gets knocked out, you're able to restore it in many cases. So it's, as with all these innovations, it's more expensive, but there are cases where it's necessary to go with ECC RAM. Everyone now is computing on their phones. We looked at some phone circuitry a couple of weeks ago, and you will find a different flavor of DDR-RAM sitting on your phone called LP DDR-RAM. This is low power DDR-RAM. So the traditional desktop and server market has been all about speed and performance and capacity. With phones, you have different criteria, specifically to do with power. Everyone wants to reduce power so you don't have to carry around a large battery with you so much. So we've been seeing innovations, a lot of innovations in this space in recent years. I think we're on LPDDR5 is the latest one. As with regular DDR-RAM, it's gone through several standards. We're seeing innovations like reducing the voltage that it runs at, playing with the refresh rate. At different temperatures, you can get away with different refresh rates. And ideas like only putting power into parts of memory that are actually needed. Most of the time, your phone memory is just sitting there doing nothing. It's not storing anything that's actually important. And you can actually just turn those bits off. You can cut all the power to them, and it doesn't matter if they lose what they're storing, because it's not important data. So if you can keep track of which parts of your phone's memory are actually in use, which part are storing real data that is relevant, you can set this up so we only supply power to the parts that are in use, and we'll put the rest into some kind of sleep mode. We can also put the whole RAM into deep sleep mode if the phone's just in your pocket doing nothing. So this suggests then it's good to close down all your apps on your phone when you're not using them, because they're sitting there taking up RAM, and having that RAM in use is drawing more power than if the RAM is not in use. Virtual memory is effectively a form of RAM, which you see if you're working with an operating system. You will study this more in your operating systems module, but just to put it into context here, virtual memory doesn't exist as RAM on chips. It exists as a larger address space, which includes stuff sitting on your hard disk. And the idea is you're going to pretend areas of your hard disk are in memory, in RAM, and when you need them, you're going to swap them in and out. You're going to take stuff on the hard disk and put pages of that into your RAM on chips and swap things in and out. You can think of it as another form of caching. It's the next level down in the caching hierarchy. You'll look a lot more at this in your operating systems module. There are different algorithms for deciding when to bring pages in and out. But if you're working on top of an operating system, you will see your computer as having a much bigger address space than the actual RAM that is available. And the reason you see that is because your operating system is pretending that all this stuff on your hard disk is part of the same address space as the real RAM itself. Modern hard disks are not always spinning disks now. You can have solid-state disks that look and behave much more like traditional RAM memory. So we're actually seeing a blurring of the line between what is a disk, what is RAM, and what is virtual memory. And then we get to ROMs. So a ROM, as with RAM, is a horribly misnamed concept. Traditionally in junior schools, you were taught that ROM and RAM were the yin and yang, the two types of memory, but they're not even orthogonal to each other, because most ROMs are randomly accessible. So ROM means read-only memory. You can take some ROM and you can put it in the same address space as all the rest of your RAM, and it is randomly accessible. You can go and read it at least whenever you like. So that they're not two separate categories. They do in fact overlap. Also, the concept of read-only has pretty much gone away. A lot of ROMs are in fact writable in various ways now. So by ROM, we traditionally we mean a chip that has been pre-printed, it's been fixed what's on the chip, it's storing programs and data, and it's mounted in the address space of the machine. That definition doesn't always hold now. You might have ROMs like your flash memory stick might be considered a ROM, but that isn't part of the address space. That isn't being randomly accessed anymore. And your flash memory stick is also rewritable, so it's not really read-only. But traditionally, we mean things like this. This is a BIOS chip. This is a very basic program that is physically built into your computer when you first turn it on. It's going to run the basic input-output system before your operating system starts up. And so because that's the first thing the computer loads, it has to be stored in ROM because you haven't loaded any device drivers yet to tell you how to read stuff off a hard disk. So the most basic functionality of the computer is going to be in ROM. In the old days, in the 8-bit era, everything in your proto-operating system would be in ROM. There'd be all these library functions you could call that were mounted at known locations. So traditional ROM is called mask ROM. This is ROM that's been produced using photolithography. That's the screen masking process that we saw before. Very expensive to produce, right? Millions of dollars every time you make one of these designs. Don't want to get it wrong. Because of the cost of producing them, we went to programmable ROMs. So these are chips that are manufactured in a generic way, and then you burn in almost firmware to the ROM. You can burn programs and data onto it once, and then it's fixed. So this means you can separate the manufacturing process from the particular program that's going to be put on there. So if you write your program and get it wrong, you can just chuck out the one chip that you burned it on and take another identical chip and burn the fixed version instead of spending $5 million on a new set of masks. Then we got to erasable PROMs. So this is like the PROM, but now you can erase the whole chip. If you put it in a special machine and shine ultraviolet light on it, that will erase everything, and you've got a new blank chip that you can burn a new program onto. Now, these kinds of things were used a lot in the 8-bit era. If you were a small computer company like Acorn and you needed to make a custom ROM, you probably didn't want to spend $5 million on a set of masks, but you could buy in a load of these quite cheaply and then just burn on your own firmware. Then we got to EEPROM, which is electrically erasable PROM. This is the same idea, but it's easier to erase. You can do the erasing electronically instead of having to lift it out of your computer and putting it in a machine with an ultraviolet light box. It could just be done by flipping a switch or done programmatically. And this has now evolved into flash memory. This is the kind we see on our memory sticks or our solid-state hard disks. This is EEPROM, which can be erased electronically on a segment-wise basis. You don't have to erase the whole ROM at once. You can erase just some part of it. That's how you delete a single file sitting on your flash stick. So the concept of ROM has really changed, and it's highly debatable whether this should be considered read-only at all. And it's debatable whether these devices, but it's not debatable, they just don't. They don't sit in the address space. They're not randomly addressable like traditional ROMs like this used to be. So ROM concept has been just about as flexible as RAM in the way that we all abuse it. So, caches. We've talked about the memory hierarchy, okay? We have all these different technologies which can store things either small and fast or big and slow. And what we would like to do is have this hierarchy so that, like on our desk, stuff that we're using, that we're working with, is close to us, and as you go further away, you're getting bigger and slower storage. So we'd like to be able to make copies of things. We'd like to take stuff that is low down the hierarchy, and when we think we're going to need it, we're going to make a copy of it somewhere higher up the hierarchy, okay? And eventually it's going to get right up into the registers of the CPU where it's actually being used. We have to decide which elements of data and programs we want to do this with. What do we want to cache? So we can consider what is called the principle of locality. Statistically, it is possible to predict which bits of memory are likely to be needed in the future. We have temporal locality. That means if you hit on a piece of memory, it's very likely you're going to want to hit on that same piece of memory again, okay? I just read something, I'm either going to read it again or I'm going to write it again because it's in use, it's in play. Sequential locality. If I hit on A, B, and C in memory, it's very likely I'm going to hit on A, B, and C in the same order again. This is because lots of computer programs are written using loops, other kinds of repetition or iteration, and it's very likely we'll do the same bunch of things again that we just did before. Then we have spatial locality, which is that values nearby in memory tend to be accessed together. This is because nowadays it's because people who write compilers tend to put things together. If we've defined an object or a data structure, we're going to shove all that stuff in memory, we're going to take a continuous region of memory and we're going to use that to pack our data in. We don't have to do that, but it's a convention that everybody uses. So we can use these three forms of locality to quite accurately predict which parts of memory are likely to be in play. This applies both to instructions and data. They have slightly different characteristics. In particular, data is often written and read as part of this, but it's unlikely that instructions are written as well as read, unless you're doing weird things with self-modifying code, or unless you're dealing with things like operating systems that are loading and moving programs. Usually the instructions will be fixed, so you'll have a different kind of cache system that is only trying to speed up the reading for instructions than one that works with data. So the general idea of a cache then, it's a fast piece of memory that you place between a consumer of memory and a big store of memory, okay? So with the technology that we've seen, this is probably DRAM, this is probably SRAM, this is the CPU with the fast registers on it. And we're going to keep a copy of some small subset of what's in memory. It's the working set that the program's actually got in use. The word cache is an archaic English word. You sometimes hear it used for a store, a cache of pirate treasure that someone's dug up, or a cache of food. If you're a secret agent, they fly people into conflict areas and they bury caches of food at secret locations, and you can go there and dig up a cache of food or weapons to help you being a secret agent. That's the concept they're trying to bring into the computer memory concept. It's a store. It's a small store of important stuff between your consumer and your provider. So the classic cache is this one, sitting between CPU and RAM. The concept of caching occurs at all levels of the hierarchy. You know, virtual memory, even when you're writing data science code that's pulling terabytes of stuff off a hard disk and storing it in RAM for a while, or even off a remote hard disk and putting it on a local hard disk, you always have this caching concept. We can have more than one level of cache. So we might, for example, have our CPU. We can have what's called a level 1 cache, which is close to the CPU. It's still quite small. It's still very fast. Typically, level 1 cache will be split into a data cache and an instruction cache, yeah, because these have different characteristics. We don't usually write instructions. You'll also see something called a TLB cache. You'll learn about this in operating systems. This is a specialized cache for helping you with virtual memory storage and page tables in operating system. So beyond that, we will get other caches. We'll have a level 2 cache. Nowadays, we might have a level 3 cache as well. And each of these caches is going to use a different technology. They might all be based on SRAM, but you can do your caching process in different ways that I'll talk about in a sec. And those different ways are amenable to different sizes and different speeds of these caches. So they could all be built out of SRAM, but they're using different cache policies to give different behaviors. And then you have main memory sitting up here. So just an example, my current laptop, it has 16 registers. It's got 256 kibibytes. We have to call this now in level 1. It's got 2 mebibytes in level 2 and 6 mebibytes in level 3. If you want to see your own computer's CPU and memory info, here's a command you can type into a Linux terminal that will give you similar numbers to this. Okay, so how do we build caches then? We can use the same technology like SRAM in different ways to implement different caching algorithms that have different trade-offs between speed and size. This is what a cache looks like. It's a new area of memory. This isn't the main address space anymore. We have what are called tags. So a tag is anything that identifies some data, and the data is stored in what's called a block. Typically, a block is going to be several words, several contiguous words copied in from memory. In this case, we've got 3 words of 8 bits each. And you might have what is called the dirty bits. The dirty bit tells you whether the data has been modified or not. If this is variable x, and my program says let x equal 7, that's going to write to the version in the cache before it writes to main memory. The dirty bit keeps track of the fact that that write has happened, and then someone has to deal with how to copy that back into main memory. If anyone knows the song Dirty Bit by the Black Eyed Peas, that's probably the most obscure piece of computer architecture ever to have charted in the UK top 10. They like their dirty bits. We can talk about the concept of hitting and missing then. If you ask for a piece of memory, can I have address 0AFF, please? Was it in the cache? I've got all this fancy technology that's trying to predict which bits of memory need to be cached in advance. If everything works, I'm hitting on it, and I'm going to get my data out of the cache instead of going to main RAM memory. If I miss, then we have to stall what the CPU is doing, go out to main memory, bring a copy in. So we can talk about the hit and miss rate. That's how often the two things happen. The hit time, that's how long it takes to do an access if you're successful. And the miss penalty is how long it takes if you're unsuccessful, and you have to go out and bring the stuff in from main memory. And we sometimes talk of victims. When you bring something into cache, something else has to die. We've got to pick on something and remove it from the cache. That's called the victim of the cache. Who are we going to overwrite when we're bringing a new piece of data in? So there are different ways we can set up the cache that will give us these different trade-offs between speed and size that we can implement in digital logic. They're based on the idea of hashing. It's all about how we make these tags, and it's about which line we store which tag. If I've got this particular tag, am I going to store it in the top line, the second line, the third line, or wherever in the cache? A hash function is a function which maps a big datum to a smaller one. Okay? So I can define any function. For example, here I'm taking a 2-byte, 4-nibble hex code, and I'm mapping it onto a 2-nibble hex code. That's reducing the amount of information. Another way of doing a hash would be, for example, ANDing all the binary digits together. Here I've got 8 bits going in and only a single bit coming out. So a characteristic of a hash function is you can't usually recover the original input from the resulting hash data because you're making it smaller. Actually, an AND gate is the simplest form of hash. Remember we talked about AND gates being non-reversible. You can't reconstruct the input from the output because the output is smaller. So I'm going to tell you about 3 different cache mapping algorithms. These are policies for deciding what should go in your cache and where it should go in your cache, called direct map, fully associative, and set associative. So in a direct mapped cache, this is the simplest form of cache. We are going to take the address of memory. So I'm asking to read address 08F4 in this case. This is main memory. These are all the addresses. These are the contents. These are the words being stored. Okay? This is my cache. These are the lines of my cache. In a direct mapping algorithm, I'm going to take the address. I'm going to apply a hash function to it. And I might have a hash function so that this thing gets mapped to the number 1. Okay? So there's a lot more possible inputs than there are outputs. In this case, there's only 2 lines in my cache. And so whenever this address gets asked for, I know I'm going to put that in line 1. This address always goes in line 1, but so do about 100 other addresses. They'll always appear in line 1. This address will never appear in line 2 or any other line. This one has a unique relationship going to that line. So this is easy, it's fast, and it's cheap. I'm going to take the address. I just run a simple hash function that tells me which line to look in the cache. If the thing's in the cache, I'll read it from there. If it's not in, I'll bring the thing in from memory and make a cache there. The problem is you might have a program using 10 variables that all happen to have the same hash function, and they'll all be wanting to go in line 1 of cache. And then you won't get your speed up anymore because every variable we're hitting on will be competing for the cache, and we're swapping things in and out. So the other extreme we can go to is what's called a fully associative cache. In this kind of cache, we allow any address to go in any line of the cache. So you can have some policy for choosing victims. You might say, okay, we want to do a read of 08F4. You might say, which line of the cache hasn't been used for the longest? Okay, if you're not using a piece of data, like the books on your desk, that's probably the thing you want to get rid of or send back to the shelves on the library. So this is nicer because you now have more control over what is in the cache. You can try and keep the cache full of nice, useful stuff. The downside is you need a whole load of extra hardware to actually do this, because now instead of computing a simple hash function and it taking you straight to the cache line, now you have to go through your cache, probably in parallel, because the whole point of this is to be fast. You have to go through your cache, and when someone asks you for 08F4, you've got to check each line whether its tag matches the address that you're asking for, okay? In the direct version, we just go straight to line 1, because that address always goes there. In this one, you've got to have a whole bunch of digital logic attached to every line and check whether the line matches this thing you're looking for. So this kind of cache, this is going to be faster, but it's going to take up a lot more digital logic. So we're typically going to use this for the higher levels of cache. This might be how you make an L1 or an L2 cache. Okay? Whereas the direct one is going to be found lower down, maybe an L3 cache. Maybe for L2, for example, you can take this hybrid approach. This is an attempt to combine some of the advantages and drawbacks of both of those methods. In a hybrid cache, also called a set associative cache, we divide the lines of the cache into what are called sets. So you have a whole bunch of addresses will map to the same set. So this is similar to the concept of a single address going to a single line, but now it goes to a set of lines. Maybe there's 5 possible places that thing could be stored. And then within each set, you're going to do the associative search. Okay? So it's a trade-off between the direct style and the fully associative style. We can take this number, that's going to say this goes in set 3, and set 3 might have 10 lines in it. So when we look this up, we know we've got to go to set 3. We don't have to check everything in the cache, so we don't need all this tons of digital logic testing every line. But we will test 10 lines if they match. The hash will take us straight to those 10 lines. We spend money on digital logic to check each of those 10 lines. So it's a trade-off. You can check every line in the cache, you can check just one line in the cache, or you can do the hybrid and check a bunch of 10 in the cache. And typically you're going to use these 3 methods for say the 3 levels, level 1, 2, and 3 of cache, because you're trading off speed versus size. When we get to cache writes, there's some additional complexity. Everything we've talked about so far is just for cache reads. We also need to write things. At least when we're working with data, we need to do cache writes quickly, not usually for instructions. We have the same concept. We can use the same lines of cache, but now we have this concept of the dirty bit. So if I set x equals 7 in my program, I'm going to ask, has x been brought into the cache? If it's not been brought into the cache, I'm probably going to have to bring it in from RAM. Okay? Even though I'm writing this thing, I'm still going to bring it into cache. And I'm going to write it in the cache. I'm going to put the number 7 in here, and I'm going to set the dirty bit to 1. To say this thing has been changed, it's been messed with. And then again, you can have different policies, different levels of cache might want to do this differently. How exactly do we want to send this information back to the main memory? There's 2 main approaches to this. There's what's called write-through. So this says you do your write in the cache. That means it's immediately available for any other instructions immediately that want to come and read that data, and maybe some short time afterwards there's going to be a bit of digital logic that can go at quite a leisurely speed. It can say, look for anything with the dirty bit, go and transfer that back to main memory. You can set the dirty bit back to 0 once the transfer is complete. Or you can take what's called a write-back approach, and this says you just keep the thing in cache for as long as you can, and you only do the write-back when you get victimized. If someone else comes and kicks you out of cache, then you really need to write the thing back to main memory, otherwise the data will have got lost. So again, there are trade-offs here. The write-through is going to take up more bandwidth. You're spending more time pinging stuff between the 2 memories. The write-back is going to require less bandwidth, but it's going to be slower at the time it happens, because your CPU will stall at that process of victimization when you have to then wait for the thing to go back out there. Some modern CPUs will provide special instructions that let you bypass all of this. Again, this can be a reason for choosing to write in assembly code, or at least to be very careful choosing your compiler into assembly code. If you know that the data you're writing isn't going to get read very soon, you might not want to use this system. You might want it to write directly into DRAM and not spend time in the cache first. So if you really know your architecture and you want writes to go fast, you can call special, differently named instructions in your CPU and say, don't use the cache for this write, just pipe the thing straight into main DRAM.